So tonight is really the first of two talks, and it's about, art and physics talks, or I was kind of talking about like the convergence, right? And it is neat when like the art and the sciences come together. And that's also something that I've learned kind of hanging out with some of my art instructors at the college and colleagues of, actually how much there's an overlap of those things that we don't always think about. So we're going to hear more about that tonight. And tonight is about the light. So tonight's focus is about the light. So I'll be back at the end, hopefully to try and get some good questions for you. So if you have questions, think about them, hold them to the side, and we'll capture those at the end. And with that, I'll hand it off to Shelly and Jamie. So thank you.
Woo-hoo. All right, thank you all so much for being here. How many of you have ever taken a physics course? How many of you have not? After tonight, you'll all raise your hands. No, absolutely not. So I was thrilled and honored to be able to do this talk with Shelly and have her bring me in and showcase so much of her art. I'm hoping that after my short talk that you'll have a slightly different perspective when you again walk the halls and look at her pieces and hear how she was inspired to create all of them. So are we ready to dive in?
Yeah.
So what is light? I mean, we have a light on right here. Isn't it just light? There's still light outside, sun setting, light goes on, light goes off. Most of you probably don't think about light very often. It's just there. It's something that's around us. It's very critical to our entire existence. It's what allows us to live. It's what allows plants to grow. But we don't think about it a lot. Well, at least not most people. So here's the dictionary definition. So something that makes vision possible, okay? The sensation aroused by stimulation of the visual receptors. Basically just a restatement of A, okay? We can see stuff. Electromagnetic radiation of any wavelength that travels in a vacuum with a speed of 299,792,458 meters, about 186,000 miles per second, specifically such radiation that is visible to the human eye. Not very awe-inspiring. This is, it sounds really dry. You probably fell asleep after the second word. Yeah? Okay, well, I'm going to give you a brief history of light because luckily, physicists for ages have continued to ask why. And one of the things that scientists do, and physicists in particular, is we try to simplify things. We're just big kids stuck in the why phase, and we always want to understand things that are really simple to explain level. So as a theoretical physicist, one of the things that we do is we create models. And these models allow us to ignore a lot of other things so that we can understand really complicated ones. And so something that you'll hear in Shelly's talk as well is something called a spherical cow. And the spherical cow is a way for physicists to ignore the fact that cows have legs and fur and a bunch of other weird shapes. So when physicists talk about things, we often just think, okay, it's a ball. And then we can figure it out and we can study it. So the history of light began, we didn't really even understand why we could see. Ptolemy and back in kind of the BCE era thought that we had actual laser beam type rays come out of our eyeballs and capture the images of things out in the world around us. No. Luckily, 1,000 years later, Alhazen, who was a prolific scientist from Basra, realized that no, we don't have these little laser beam rays coming out of our eyes. They're coming to our eyes. So we have these rays of light that come to us. And this became the foundation of optics for hundreds of years. This idea that, these things come, light reflects off of surfaces, and that is part of why we see it. So when we get to the era of Newton, the guy with the apple, I'll go back one slide. That's supposed to be Newton. He did a lot of experiments. He was definitely a big kid stuck in the Y phase. He went so far as to try to figure out how eyes worked by sticking a needle in his eye. Because he didn't know if colors came from outside or from inside the brain. So he actually ended up discovering a lot for eye doctors for that reason. But using this idea that rays of light come and reflect off of objects around us and then come into our eye and then we interpret them. And specifically, when white light, and like light from the sun comes through, if you send it through a prism, you can actually disperse it into the rainbow. So that light is actually made up of these spectral hues, what we call the rainbow. He, however, thought that light was like a little particle, like these little guys that just kind of float off. So you have like a little purple thing hit you, and you have a blue thing hit you. There was a guy that was working at the same time named Huygens, and he thought that light was a wave, except that he wasn't as popular as Newton, so no one believed him. And so that stayed put for a couple hundred years. Then another scientist came along, and he proved, nope, light is actually a wave. And so light is actually floating through. And that then went on. So we had Young figured out it was a wave, and then a guy named Maxwell started out like, oh, it's not just a wave. It's electricity going like this. It's magnetism going like this. And they work together to create an electromagnetic wave. Can everyone do this? Coordination. Depends on how much champagne you have. Yeah. And they also started realizing that not only is it this electromagnetic wave, but it moves really, really fast at the speed of light. But that wasn't the end of the story. So is it a particle or a wave? Well, Einstein decided to really screw us all up. He said, it's both. Depending upon the situation, light can act like little chunks of energy, these little particles called photons. But in other situations, it's a wave, and it exhibits wave-like behavior, just like sound waves or ocean waves. And so there's this wave-particle duality that we actually now have to deal with. And so one thing that scientists aren't really good at is this type of ambiguity. It's like, wait, no, but what is it? It's, no, it's both. And this was the birth of quantum mechanics. The idea that it could be both simultaneously a particle and a wave at the same time. So there's this duality that we have to deal with, that we have to be comfortable with, even if we're not certain what's going on. And sometimes only until we observe the actual experiment do we know which it was. So Einstein said, it seems as though we must use sometimes the one theory and sometimes the other. Well, at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomenon of light, but together they do. And so this brought us all the way into the early 1900s and the birth of modern physics. So now, with this understanding, so now you get to raise your hand and say, I've taken physics. How does light impact how we perceive the world around us? We can only see a little bit of it. This electromagnetic spectrum that's doing this, and I'm hoping that you guys kind of just walk around town doing this at some point, because I do in my classes. The electromagnetic spectrum actually has a really wide range, all the way from the ultraviolet that we worry about burning our skin, to the infrared that we use to heat things up. And visible light, from violet to red, is only this little chunk. So there's this entire part of the world that we can't actually see. But there are a few ways that we can see it, and I'm going to go through, and again, once you're walking through and looking at the paintings, and when you hear Shelley talk later, I want you to think about what phenomenon is happening that creates each of these beautiful images. So the first is reflection. So when light rays, and again, this could be particle or waves, hit a surface, they bounce off. Easy peasy. So we see this light right here. So it bounces off, and it bounces off at the same angle that it bounced in at. We see this with mirrors. If we're standing right in front of a mirror, we see ourselves. But not every surface is smooth. If light hits a smooth surface, it just bounces off like a mirror. But if it's a really, really rough one, it makes the entire surface glow in something that's called diffusion. And this is what diffusion looks like in nature. All of these light rays are hitting and bouncing off at different angles because the surface has different angles. And so you get this beautiful, sparkling, kind of ethereal moonscape. Diffusion also causes things like sunsets. As the light scatters off of not the dust particles necessarily, but the actual molecules of nitrogen and oxygen that are in our atmosphere, it bounces off at different angles. Now, the blue scatters the most. So when the sun is up high, that's why the sky is blue. But as the sun sets, the light has to travel farther to get to us. And so as it travels farther, it scatters more. And that leaves behind those reds and oranges. Now things get a little weirder. We have refraction. So light bouncing off of something, great. But light can also go through things. And when it goes through things, it can bend. And so this is why we have this great optical illusion of a broken pencil when we stick it in water. It's because when the light transitions from air to water, it slows down and it bends. So here we again see our nice little handy dandy laser. So you see reflection on 2 and 5. It refracts, it bends down at 3, and then it hits another surface and reflects, and then it bends again and comes out. And it can do things like this. Has anyone ever seen a sundog? They're actually really common here, so hopefully you'll keep an eye out, especially when there's ice crystals in the air. And these happen at exactly 22 degrees, and they will be symmetric on either side of the sun. You'll see these beautiful, what look like slightly kind of iridescent rainbow fake suns. And that happens because of refraction off of ice crystals, when they align just right in the atmosphere. And almost everyone's favorite is dispersion, especially if you're a Pink Floyd fan. Generationally, I can tell who I'm speaking to if that hits. And so just like with Newton, we get dispersion where when light hits a prism, it goes through glass. Glass is thicker than air, so it slows down the light and it bends it. But depending upon the hue of the light, it bends more. So the reason you get a rainbow is because red light bends at a different angle than blue light. And so each of them line up and they disperse out into that rainbow. And then we can see this. So now you've got both the beautiful dispersion, but you also have that refraction and getting that additional one. And it happens at exactly 42 degrees. But it takes billions of these little raindrops all lined up just right with the sun at just the right angle in order to create these rainbows. They are that special. Put on your glasses. Because not only can you disperse light, you can do something called diffraction. And you don't have to leave them on for the rest, just put them on and I want everyone to look up. Because it's way cooler to actually see it in person. What you're seeing is white light being dispersed, but also diffracted. And what diffracted means is we had reflection, it bounces off, refraction, it bends, diffraction, it goes through and around. So it's like going through little holes. Yeah, go ahead and take them off before they give you a headache. They're great at burning in. But besides kind of cool raver glasses, diffraction also gives you images like this, where you get that silver lining in the clouds. Because light is literally going through gaps in the clouds and going and bending around it as it comes out and creating that glow around the hole. And then it gets dispersed in those, again, those particles in the air, creating beautiful beams. And now you get diffusion on the surface of the water. So all of these effects stack up to give us these beautiful images. Now, that's a lot about clouds. But what about things like actual physical objects? The reason that we see colors is down to two things, either refraction or reflection. When it's reflection, it's because this bird is actually red. It has pigment because of its diet and genetics that make it red. Light hits the bird, it absorbs every other color but red, and red bounces off and into our eye. The hummingbird on the left is not rainbow. That is not real color. That is actually refraction. So that is a result of the structure of its feathers, or in the case of a butterfly, of its wings. Or in the case of someone with blue eyes, they're not actually blue. It is refraction of the light and the way that it interacts with the surfaces, just like these glasses. And the only thing that gets refracted back to us is blue. Right? Yeah? Okay, good. I like that. And there's one other thing that I really like covering, and that's bubbles, because this is interference. And so again, this is that wave nature. So if waves are traveling, we've seen it if we're looking at ocean waves. If they combine, they become big. It might become a tsunami. But if they go opposite, they actually flatten out. You get this with sound too. This is what happens with bubbles. They're thin films of soap. And as they're floating, they're feeling the effects of gravity. They're evaporating into the air, so that thickness of that soap film is changing. And so the waves that are reflecting or refracting through that film is also changing. And so we get dispersion, we get reflection, we get refraction, and then we start getting black spots. As they get really thin, the waves start to interfere with each other and they collapse and they cancel out, and that's when we get black spots and bubbles right before they pop. And the last thing I want to talk about, because I don't want to take too much time, is mantis shrimp. And the reason I want to talk about mantis shrimp is because they're incredible. Now, we only have 3 color receptors. So we can just receive red, green, and blue. And then our brains and the way those combine create the spectrum that we can see. These guys have 12. They can see polarization, they can see ultraviolet. So can you imagine if you were a mantis shrimp walking around and looking at an art exhibit? So that is what I want to do.